The galaxies are considered as the building blocks of the universe in its large-scale structure perspective. Most of the galaxies including our galaxy Milky Way are normal galaxies as their light comes from the million to trillion of its constituent stars, distributed in pattern throughout the galaxy. But if we look at some galaxies, we see intense light coming from their nuclei, those are active galaxies. Active galaxies appear as stars-like sources but partly show non-thermal spectra. That concentrated non-thermal spectral emissions actually comes from the central part of the galaxy named as active galactic nuclei, AGN. The active galaxies are a small fraction, 1 to 10%, of all galaxies in the universe, and their bright compact nuclei are of size less than 1017 centimeters, Edelson et al., 1996, with a high luminosity, i.e., 1042 erg/sec. The study of AGN is one of the most dynamic areas of contemporary astronomy, which includes around one-fifth of astronomers. The most key driving force of large luminosities of light from the compact central regions is due to the presence of supermassive accreting black holes, SMBHs, at the center of the galaxy. It is the central engine of the AGN. The continuum radiation of AGNs extends over an extraordinarily broad range of frequencies from the highest energy rays to the lowest energy radio waves. The spectra of these objects contain very broad and strong permitted and forbidden lines such as Li, NV, SIIV, CIV, CIII, MGII, and Balmer lines. Other important reasons for studying them was to understand the physics of their luminosity and high redshifts, making them excellent probes to study the early universe. It was also recognized that the AGN's luminosity would outshine the luminosity of all the stars of the host galaxy and was emitted from a region geometrically confined to small region, 10-2 pc. Hence AGNs were recognized as astrophysical laboratories for studying the extreme physical conditions of space such as hot plasma, magnetic fields of black holes, and relativistic motion. Understanding AGN structures is crucial in astrophysics, as these cosmic powerhouses play a vital role in the evolution of galaxies, the dispersion of heavy elements, and the regulation of star formation within their host galaxies. AGNs have a compact nuclear region emitting significantly beyond what is expected from stellar processes. It shows a clear signature of a non-stellar continuum emitting process in its center. The radiation of AGNs is mostly non-thermal and hence might be produced through physical processes different from thermonuclear reactions which power the stars. AGNs are known to show variability since their discovery, and it is considered as one of their defining properties. Rapid continuum and line flux variability may be seen over a time period of few hours to years throughout the electromagnetic spectrum. Structure of AGN. Active galactic nuclei, AGN, are some of the most energetic and enigmatic objects in the universe, found at the centers of galaxies. They are powered by the presence of a supermassive black hole, which can be millions to billions of times the mass of our Sunday. The structure of AGN is a complex interplay of various components, each contributing to the immense energy output observed across the electromagnetic spectrum. The detailed structural analysis of AGN involves understanding of following key components: central supermassive black hole, SMBHs. At the heart of every AGN lies a supermassive black hole, which is the primary source of its enormous amount of energy. The immense gravitational forces exerted by the black hole is due to its infinitely dense compact high mass, 103 to 106 m, which draw in surrounding matter, leading to accretion. As matter falls into the black hole, it releases a tremendous amount of energy, resulting in the AGN's luminosity. The evidence of presence of SMBH at the center of an active galaxy comes from optical and radio observations which show a sharp rise in the velocities of stars or gas clouds orbiting the center of galaxy. High orbital velocities mean that something massive is creating a powerful gravitational field which is accelerating the stars. X-ray observations indicate that a large amount of energy is produced in the center of many galaxies, presumably by the infall of matter into a black hole. Accretion disk. As material spirals inward toward the black hole, it forms an accretion disk. The disk is a flattened, rotating structure composed of gas, dust, and other matters. The matters rotate with a very high speed in the central plane of the host galaxy, obtaining most of its angular momentum. The gravitational forces and friction within the disk heat the material to extremely high temperatures, causing it to emit intense radiation, particularly in X-rays and ultraviolet light. This radiation arises from the conversion of gravitational potential energy to kinetic energy of gas and thermal energy within the accretion disk with an efficiency about 4 to 42%. The accretion disks can be of type thin, slim, and thick disks on the basis of their shape. Depending on the column density and level of ionization of gas, the disks can be optically thin or thick. The geometrically thin and optically thick disks are easier to treat analytically as well as numerically, so grabs the attention of most astrophysicists working on AGNs. Broadline region, BLR, close to the central black hole, a region known as the broadline region, BLR, contains ionized gas, primarily composed of hydrogen, although it can contain other elements as well. These clouds are thought to be patchy and clumpy, rather than a continuous and uniform medium. The intense radiation from the accretion disk ionizes the gas in this region, leading to the emission of broad spectral lines. The broadening of these lines is due to the high velocities of the gas within the BLR, with some portions of the gas moving towards the observer and others moving away, leading to a Doppler broadening effect. Line profiles of BLR emissions are often asymmetric and exhibit characteristic shapes, such as broadened Gaussians, which allow astronomers to study the motion and ionization of gas within the BLR, properties of the central black hole, such as its mass and accretion rate. By studying the velocity, 1000 to 10,000 km per second, and broadening of the spectral lines emitted by the BLR, astronomers can use the virial theorem to estimate the SMBH's mass. One of the intriguing aspects of the BLR is its variability. The emission lines from the BLR can change in intensity and profile on various time scales, from hours to years. Narrow line region, NLR, beyond the BLR, the narrow line region, NLR, contains ionized gas emitting narrow spectral lines. These lines are narrower than those from the BLR and result from the radiation that permeates the outer regions of the AGN. The NLR is thought to be a more extended region than the BLR, spanning tens to hundreds of parsecs from the central black hole. It is often believed to be clumpy, consisting of clouds or filaments of ionized gas and can be distributed both spherically and in a flattened disk-like structure. The narrowness of these lines typically results from the lesser velocity, 100 to 1000 km per second, and thermal motion of the gas. Such narrow emission lines are characterized by their symmetric and narrow Gaussian profiles. Like the BLR, the NLR can also exhibit variability in its emission lines over different time scales. The NLR provides information about the surrounding environment, temperature, metallicity, and its response to the central AGN. Dusty torus encircling the central regions, there's a donut-shaped structure called the dusty torus. The dusty torus consists of gas and dust, and its orientation can influence the classification of the AGN. If the torus obscures the central region from our line of sight, it can result in the AGN being classified as Seyfert galaxies. In contrast, if the torus is viewed edge-on, we may observe a quasar or a blazar. Relativistic jets, some AGN, known as radio galaxies, quasars, or blazars, exhibit powerful relativistic jets that emanate from the vicinity of the central black hole. These jets are composed of high-energy particles that move at nearly the speed of light. Relativistic jets emit radiation across a wide range of the electromagnetic spectrum. They are often brightest in radio wavelengths due to synchrotron emission by high-energy electrons moving in a strong magnetic field. Additionally, they can produce gamma-ray radiation through inverse Compton scattering, in which high-energy electrons collide with lower-energy photons, boosting them to gamma-ray energies. One of the most remarkable aspects of relativistic jets is their extreme collimation. These jets can maintain their narrow beam-like structure over vast distances, often extending thousands or even millions of light-years. Relativistic jets can have a profound impact on their surroundings. They can influence the interstellar medium and the star formation in their host galaxies. The energy and particles released by the jets can create shock waves, heating the surrounding gas and triggering the formation of stars. In some cases, relativistic jets can be associated with large radio lobes, which are regions of enhanced emission surrounding the jet formed in pairs, more or less symmetrically about the nuclei with a linear extent of several megaparsecs.